Okay, an aldose is an aldehyde group at the top of the sugar. A ketose is a ketone group at the top of the sugar. Okay, so here's your sugar molecule. This is your Fischer projection. Okay, your most oxidized end is at the top. If this group above the carbonyl group is an R group, like it is methyl here, this is a ketose. If it's a hydrogen, it's an aldose. Okay, so this is a ketose. And this is D-ketose. The D refers to the polarization of light, which way it rotates polarized light. If the OH group on the bottom, the one closest to the non-oxidized end, okay, the least oxidized end is the bottom part here. The chiral carbon at the bottom of that chain, if the OH group is on the right, it's a D. If this is on the left, it would be an L. It stands for dextrorotary and levorotary. It's the way it rotates visible light. Okay? And we'll get into how to determine that in just a minute here too. So that's D, keto, tetrose. So D means the OH group's on the right. Keto means it's a ketone, which right here is there's two carbonyl groups attached to this. There's two R groups attached to the carbonyl carbon, so it's a ketone. And it's a tetra, which is four. So there's 4 carbons. And it's an ose, which is a sugar. So the name tells you everything. It tells you where the OH group is. It tells you whether it's an aldehyde or a ketone group. That's the most oxidized at the top. It tells you how many carbons are in the chain, and it tells you it's a sugar. This one here. This one has a hydrogen here. This is an aldehyde, so it's an aldose. Okay. The OH group is on the left side here, so it's an L, aldose. And how many carbons are in the chain? 1, 2, 3, 4, 5 carbons. So it's a pentose. Okay. So it tells you the information about the chain. It's an aldose, which you said. And the official name is L-aldo pentose. So the L means a OH group is to the left, levorotary, versus dextrorotary, which is on the right. Aldo means it's an aldehyde group attached to the carbonyl carbon. Okay. Penta means 5, ose means sugar. So a pentose is a 5-carbon sugar. Okay. And this one here, let me get some of the writing out of the way. Is this one here an aldose or a ketose?
Ketose.
Perfect. It's a ketose. Okay. And is it a D or an L?
D.
It's a D because the OH group is on the right, the bottom OH group, the bottom, the lowest chiral carbon. We did chiral carbons, right? I think we did that several chapters ago. But a chiral carbon, there's 4 different things attached. So it's the lowest chiral carbon where the OH group is on there. That is a D or an L. So this is a D. Okay, and there's 1, 2, 3, 4, 5, 6 carbons. So it's a hexose. Okay, so it's D, keto, hexose. D means the OH group's on the right for the lowest chiral carbon. Keto means it's a ketone group attached to the top. Hexose means it's a 6-carbon sugar. Okay. Once we get these names down, we're able to draw these out and how they're typically found in the ring forms when they're found in the human body for biochemistry. Again, aldose or ketose. This is a aldose. Okay. And so this is an aldose. Okay. The OH group on the lowest chiral carbon is on the right. So it's a D. And there's 3 carbons. So it is a triose. So it's D, aldo, triose. Okay, it's an aldose. and it's D-aldotriose. Okay, this is a ketose because there's a ketone group on the top here because it's carbonyl carbon. There's two R groups attached to it. So it's a ketose. There's 1, 2, 3, 4, 5, 6 carbons. Okay. So it is a hexose. Okay. And the OH group on the lowest chiral carbon is to the right. So it's a D. So it's a D ketohexose. So it's a ketose, as we said, and D ketohexose. Okay. Hey, aldehyde, is it aldose or ketose? The one on the right now.
Aldose.
It's an aldose because this is a hydrogen here. It's an aldehyde group. So it's an aldose. Yeah, I think the name. Yeah, it's an aldose. And 1, 2, 3, 4, 5 carbons. So it's a pentose. So it's an aldopentose. And is it D or L? What would it be?
L.
It would be L. Perfect. Because your OH group is attached to the lowest chiral carbon to the left side when it's written. So that's an L. So it is L, aldehyde, pentose, 5 carbon sugar. Simple sugars we were talking about. Those are all sugars. Aldoses and ketoses are different sugars. Tooth decay and simple sugars. Cause of tooth decay is plaque and the acid formed by the bacterium Streptococcus mutans, which uses sucrose as a substrate. So Streptococcus mutans exist in your mouth normally. Its food source is sucrose, is sugar. Once it gets to its food source, it builds in the mouth, and then it can release its sugars. It's an acid, which destroys tooth structure. So the fuel for tooth decay is sucrose from the Streptococcus mutans bacteria, which is a normal inhabitant of the mouth. Saliva is teeming with bacteria and concentrations up to 100 million per milliliter. So every milliliter of saliva has about 10 million bacteria in it, which is a lot. So within minutes after you brush your teeth, sticky glycoproteins in the saliva adhere to your tooth surface. That's what the bacteria adhere to. Okay. Then millions of oral bacteria immediately bind to the surface. Okay. You always have this plaque being formed. Although many oral bacteria stick to the tooth surface, only Streptococcus mutans causes cavities. That's the one that has sucrose as its fuel and releases acid that destroys the enamel of the teeth, eats away at it. The reason for this is that the organism alone can make the enzyme glycosyltransferase. Glycosyltransferase acts on the disaccharide sucrose, and it breaks it down into glucose and fructose. So it's the only bacteria that can use sucrose as an energy source because it has the enzyme that breaks down sucrose. Sucrose is a disaccharide. You need to break it down to monosaccharide to your energy source, glucose and fructose. Okay. The glucose is immediately added to a growing polysaccharide called dextran. The glue that allows bacteria to adhere to the tooth surface contributes to the formation of plaque. Okay. Now the bacteria embedded in the dextran takes in the fructose and uses it in lactic acid fermentation. So it uses the glucose and the fructose from sucrose. The lactic acid is produced, lowers the pH on the tooth, on the tooth surface, begins to dissolve calcium from the tooth enamel. Remember, lowering pH increases the H+ content. The lower the pH, the stronger the acid. Okay. Even though we produce about 1 liter of saliva every day, the acid cannot be washed away from the tooth surface because the dextran plaque is not permeable to saliva. So this plaque does not get rinsed away by regular saliva, has to be brushed off, or once it adheres and calcifies, then has to be scraped off by a hygienist or a dentist. So how do you prevent tooth decay? Brush after every meal, floss regularly, reduces that plaque buildup. Eating a diet rich in calcium helps build the enamel. Foods rich in complex carbohydrates like fruits and vegetables help prevent cavities in 2 ways. And we'll get into a lot of this detail in biochemistry part. Glucosyltransferase can't use complex carbohydrates. You can only use sucrose, only use disaccharides to break into glucose and fructose. Okay, so it cannot use the complex carbohydrates. Okay? Eating fruits and vegetables helps to mechanically remove plaque. Okay, most effective way to prevent decay is to avoid sucrose-containing snacks between meals when you're not brushing. That way, there's no fuel for the Streptococcus mutans bacteria. Studies have shown that eating sucrose-rich food doesn't cause much tooth decay if followed immediately by brushing. So you can get away with it as long as you brush right after it. However, even small amounts of sugar eaten between meals actively promotes cavity formation if you do not brush. Just sipping Coca-Cola, okay, with sugar in it between meals, anything like that, any kind of sugar compound. And if you look on X-ray, this is what we look at all day long. This is looking at X-ray. You can see little cavity starting right here and right here, those little triangles. And you see a big cavity right here. All that's decay on that tooth there. You can see it on the X-ray, the dark areas. Okay, this is what it looks like. We clean it all out. We cut everything back. We clean out all the decay. Okay, and this is the restoration, what it looks like with our new composites we use. That's the filling that's on it too. Okay, we also replace silver fillings before and after. You can make them look really nice. Okay, a lot of all the stuff we have, I haven't done a silver filling probably 20, 25 years. Everything's composites nowadays. Okay, we're talking about stereoisomers and stereochemistry. Okay, we talked about D and L prefixes. Okay, identify the two isomeric forms. Okay, they're isomers of each other, the same chemical structure, different what I'm trying to think of, same chemical compound, different structure. Well, they're isomers. Okay, isomers differ in spatial arrangements of atoms and are stereoisomers. So the atoms are the same, but they differ in their arrangement. Okay, they have the same molecular formula. Different, that's what I'm trying to say, same molecular formula, different structural formula. Okay, they have the same bonding, each one of these stereoisomers. Stereochemistry is a study of spatial arrangements of atoms, how they're arranged in space. Okay, so the D and L glyceraldehydes are what's called non-superimposable mirror image molecules, and those are enantiomers. Enantiomers are a subset of, they're a type of stereoisomer. So they're non-superimposable mirror images. So if you take your left and right hands, your left hand is a mirror image of your right hand. If you hold your right hand to a mirror, you have your left hand. Okay, those are mirror images. They're not superimposable. You cannot take your left hand and position it on top of your right hand, no matter how you move it, to form the exact same thing. They're stereoisomers. Those are enantiomers. So they're non-superimposable mirror images. Okay, and of different chemical properties. Okay. So you can take your compound, this is a chiral carbon, and this is the mirror. You see this is the mirror image of that, just like your right hand and your left hand mirror images. No matter how you position that molecule on the right, it cannot match up with the molecule on the left. Okay, if you rotate it counterclockwise, the C is going to be the opposite direction. You rotate it clockwise, the D is going to be the opposite direction. No matter how you position, you can't line it up. That's a non-superimposable mirror image. Okay. So two isomers that are non-superimposable mirror images of one another are called enantiomers. That's the term we use for it. So enantiomers is a type of stereoisomer, and it's a non-superimposable mirror images. It's a non-superimposable mirror image because there's a chiral carbon. Okay? You have to have a chiral carbon to be a non-superimposable mirror image. If you do not have a chiral carbon, then the mirror image can be imposed on top of each other. So you have to have 4 different things attached to a carbon atom to have it be an enantiomer. Okay? Molecules that can exist in enantiomeric form are called chiral molecules. They're called chiral molecules because they have to contain at least 1 chiral carbon. Okay? So the term chiral simply means the result of different three-dimensional arrangements of the atoms. Can exist in two mirror image forms that are non-superimposable. That's what chiral means. Chiral means four different things are attached. So if you look at the mirror image of it, it's going to be non-superimposable. And you'll have two forms of a D and an L. Okay. So for any pair of non-superimposable mirror images, any pair of anomers that we have, one is always designated D and the other is designated as an L. Okay. We make medications. We have D and L forms that are isomers. They make that in combination with it. Okay. So chirality, or chiral carbons. A carbon atom that has four different groups bonded to it is called a chiral carbon. Okay. So any molecule containing a chiral carbon can exist as a pair of anomers, non-superimposable mirror images. So chirality in glyceraldehyde, which is a simple carbohydrate, is conveyed by a chiral carbon. Okay. Larger biological molecules often have more than one chiral carbon of different chiral centers. Okay. This is a aldose. This is a trialdose, 3 carbons. Okay. There's only one. Okay. If I ask you on an exam, number 1, number 2, number 3, which one or which ones of the following molecule are chiral carbons? Is number 1, is 1 a chiral carbon? Is 2 a chiral carbon? Is 3 a chiral carbon? Or are they all chiral carbons? Or just there's 2 of them? Is number 1 a chiral carbon? Nobody wants to guess? Number 1 is not a chiral carbon. You have oxygen attached to 2 things right here. Remember, you have to have 4 different things attached. Is number 2 a chiral carbon? You have an OH group, you have an H, you have this attached, and you have this attached. 4 different groups. So number 2 is a chiral carbon. Is number 3 a chiral carbon? No, you have 2 hydrogens attached to that carbon. They're not different. So there's only one chiral carbon in this molecule. Okay, the OH group is on the right-hand side. So that is D isomer. Okay, so that's what a chiral carbon is. The chiral carbon in glyceraldehyde. There's only one. Okay, glyceraldehyde has a chiral carbon and thus has 2 anomers, a D and an L. Okay, the D isomer has the OH on the stereocenter on the right-hand side. Stereocenter is a chiral carbon. The L isomer has the OH group on the stereocenter on the left-hand side of it. So D stands for dextrorotary, rotates plane polarized light to the right. L stands for levorotary, okay? It rotates plane polarized light to the left when you shine a polarimeter on it. It just takes it and bends light in a different direction. Okay, and those are anomers. We have this one here, and we have this one here. That's glyceraldehyde. This is D glyceraldehyde. This is L glyceraldehyde. And they're trioses, okay, because there's 3 carbons and they're an aldose because they're aldehydes on the top, the most oxidated end. Okay, everybody sees it. No matter how you spin this one around on the right, you cannot make it superimpose the one on the left. It's not going to do it. Okay, because it can't spin 3 times. You have 4 different bonds in that chiral center. So this is your D isomer. This is your L isomer. So if you look at it on the ball and stick model, okay, again, the OH group is on the right, so it's a D. OH group is on the left, so it's an L. Okay. And we determine D and L by the chiral center farthest from the most oxidized end. So the most oxidized end always goes on top. Okay. So the chiral center farthest from the most oxidized end, farthest down, is the carbon we use to determine whether it's going to be a D or an L designation. Does that make sense? So put a thumbs up or say yes or something. So
Yes.
okay, perfect. All right, cool. Okay, and this is the ball and stick model of it. You can see the OH group here is on the right, OH group on the left. And no matter how I position or twist this molecule here, I cannot get it to superimpose on top of the other one. Okay, there's always going to be something lined up differently because there's 4 different things attached to it. Okay, optical activity. So enantiomers are called optical isomers. Optical isomers just means which way they're going to rotate plane polarized light. All right. So like we've been saying, enantiomers interact with plane polarized light to rotate the plane of light in opposite directions. One goes to the right, one goes to the left. Okay. That's called optical activity. So molecules that have a chiral center are optically active. They will rotate plane polarized light to one side or another. Molecules that do not have a chiral center will not do that. They will not have enantiomers. They won't have ones that rotate light to different directions. So optical activity distinguishes the isomers. That's what does it, how it rotates plane polarized light. We measure that in what's called a polarimeter. Okay. So polarized light is normal light vibration in an infinite number of directions, perpendicular to the direction of travel. So as light's traveling across the room, it's vibrating up and down. If it's going up and down, vibrating side to side. So it vibrates in an infinite number of directions that's always perpendicular to how it travels. Okay. When light passes through a polarizing filter, only light vibrating in one plane reaches the other side of the filter. Okay. That's how your sunglasses work. They're polarized. It takes all those vibrations of light and only lets one vibration pass through, one energy level. Okay. So polarimeter allows a determination of a specific rotation of a compound. So it measures the ability to rotate plane polarized light. Okay, and that's what a polarimeter looks like. Here's your light source. Okay, unpolarized light goes in an infinite number of directions all around 360 degrees. Light's traveling this way. The light waves are going perpendicular to that path. A polarized filter only allows one plane of light to pass. Okay, you put the sample in, it'll either rotate to the right or rotate that line to the left, depending what it is. And that tells you D or L. Okay. So when an enantiomer is in a solution, it's placed in that polarimeter that you saw, and a plane of rotation, and the plane of rotation of the polarized light is rotated down. So that light coming in that's in one plane hits it, and it rotates to one direction if it's one isomer. It hits it, rotates to the other direction if it's the other isomer. Okay, so one enantiomer always rotates the light in a clockwise direction. That's dextrorotary. It rotates right in a clockwise direction to the right. Okay, that is your D isomer, dextrorotary. The other isomer rotates counterclockwise, which is to your left, and that's levorotary. So dextrorotary and levorotary are the directions it's going to rotate plane polarized light for each enantiomer. Okay. So under identical conditions, the enantiomers always rotate light to exactly the same degree, but in opposite directions. So if one of the enantiomers rotates light to the right by 7 degrees, the other enantiomer is going to rotate plane polarized light to the left by 7 degrees. They're going to each rotate the same amount of degrees for the light, but in opposite directions. Okay. Then we're getting to Fisher projections. Use how we're going to, those are the line drawings we use, the Fisher projection, how we're going to draw those and use those to create our cyclical structures. So the Fisher projection, like I said, uses lines crossing through a chiral carbon to represent bonds. It's projecting out of the page are the horizontal lines. Projecting into the page are the vertical lines. That's how you have to think of it. So coming out of the page is your horizontal lines. Your vertical lines are the ones that are projecting into the page. It's a three-dimensional object. So compare the wedge to the Fisher diagrams. Okay. So this is your ball and stick model. Okay. This is your model that shows you which ones are going in, which ones are going out. And this is your Fisher projection. Okay. So it's just a shortcut way of doing things. It shows you which one, the same bonds as the ball and stick model as the other ones. Okay. So the horizontal lines, bromine and chlorine, are coming out of the page. The vertical lines, hydrogen and fluorine, are going into the page. Okay, and this is a three-dimensional representation of it, right? Oops, right here. So what's called a racemic mixture is a mixture of equal amounts of pairs of enantiomers. They're optically active and they're racemic. We talked about thalidomide. Thalidomide is a pair of optically active enantiomers. Half of it is D, half is an L. The D form was an anti-nausea drug. The L form was the one that caused birth defects in newborns. Okay? So they have much different effects depending which isomer it is, up to being toxic. And all of our medications are D and L. We don't separate those out. It's way too expensive to do that. Okay? So diastomers, okay, is a pair of stereoisomers having two or more chiral centers that are not enantiomers. Okay, so that's a diastomer. It's a stereoisomers having two or more chiral centers and that are not enantiomers. They're not non-superimposable in image of each other. They have two or more chiral centers. A mesocompound is a compound with two or more chiral centers and an internal plane of symmetry that causes it to be optically inactive. In other words, even though there's chiral centers, they balance out by one exact opposite on the other side. So in other words, if you had it's exactly divided through it. So they would not be, they'll be symmetrical. So if you had a chiral center, say at C, F, Cl, bromine, carbon. Okay, and if we had, let's put CH2, CH2 across there, and let's put another C, CF, Cl, and bromine. So here's two chiral centers on each end. Okay, so you think it'd be off that, but if you look at it, it's exactly symmetrical. It rotates around this line here. So this is the same as this. So even though there's two chiral centers in it, now I have a symmetrical point. So a plane of symmetry. So they are not optically active anymore because it's not going to rotate the line in different directions because it's symmetrical now. You have a plane of sense, it's exactly the same on both sides. So they basically cancel each other out. That's what a mesocompound is. Mesocompound cancels out because there's a common plane of symmetry, an internal plane. And that causes it to be optically inactive. So our D and L system, monosaccharides are drawn in Fisher projections. Monosaccharides are a single saccharide, single unit. The most oxidized carbon is closest to the top, which is our aldehyde or ketone. Carbons are numbered from the top. If the chiral carbon with the highest number has the OH group to the right, the sugar is D. Okay, this is the chiral carbon farthest from the most oxidized end. If the OH is to the left, the sugar is L. Those are all the rules we've just been reviewing. Nothing new. It's all the same thing we've been talking about. Okay. So the most common sugars are in the D form, which we utilize in our bodies. Okay. So the most oxidized, that's our carbonyl group, is on the top. Our least oxidized, our CH2OH is on the bottom. Okay. And the OH group that's on the carbon with the highest number, which means the one furthest away from the oxidized end, determines whether it's D or L. Okay. So here we have a carbon. Okay. It's the same representation. Remember, the vertical bonds are coming out of the board. I mean, going into the board. The horizontal planes are coming out of the board. Okay. So this is the most oxidized end. We have the carbonyl group, and it's an aldehyde. It's an aldose, and it's a triose. It's an aldotriose because there's 3 carbons on it. Is this an L or a D triose? OH group's on the right, so it's a what?
D.
It's a D. Perfect. It's a D. Aldo triose. 3 carbon sugar, aldehyde group at the top, most oxidized form, and the OH group to the highest number chiral carbon is on the right. So this is the D isomer of aldotriose. This is the L isomer of aldotriose. Okay. Everybody can distinguish between D and L isomers now. Okay. So Fischer knew that the 2 nanograms of glyceraldehyde rotated plane polarized light in opposite directions, but he did not have enough the tools needed to make an absolute connection between the structure and the direction of rotation of plane polarized light. But he knew they went opposite of each other. He simply decided that plus enantiomers would be the ones with the hydroxyl group to the chiral carbon on the right. These rotated plane polarized light to the plus or dextral direction. He called this enantiomer the D-glyceraldehyde. Okay. The enantiomer that rotated plane polarized light to the left, he gave a negative designation, okay, or levorotary, and called that L-glyceraldehyde. Okay. So there's a Fischer projection. Okay, the rule is the most oxidized end goes to the top. So that's an aldose. And the carbon's always numbered from the top down. So this is carbon 1. This is carbon 2. This is carbon 3. This is carbon 4. Okay. This compound has 2 chiral centers. And it's a non-superimposable mirror image, and it's optically active. Okay. So we use the carbon with the chiral carbon with the highest number to determine whether the OH group is on the right or left for D or L designation. So this is carbon number 3. This one's chiral carbon. Carbon number 4 is not chiral. So the chiral carbon with the highest number is carbon number 3. The OH group on carbon number 3 is attached to the right-hand side. Okay, so this is a D isomer. Okay, it's a D erythrose, which is a D aldotetrose. 4 carbon sugar, aldehyde group on top, and it's a D orientation. Look at this one here. This is a ketose. Okay, and it has 1, 2, 3, 4, 5, 6 carbons. So it is it's 6 carbons is hexose. So it's a 6 carbon sugar, and it's a ketose. So it's a ketohexose. And again, we're looking at the OH group on the carbon, the chiral carbon with the highest number. So in this molecule, we have 3 chiral carbons. This is a chiral carbon. This is a chiral carbon. And this is a chirocarbon. So we take the chirocarbon with the highest number, which is number 5 in this case, and we look where the OH group is. OH group is on the right-hand side. So this is a D. That's D fructose. It's a D keto hexose. Okay, is this making sense?
Yeah.
Kinda.
All right, perfect. Good, because it's going to get a little more complicated because we're going to put these into cyclic form, which actually exist in nature. I'll take a little time to show you how to draw these from the Fisher projections. So once you understand the Fisher projections, you can see how they actually exist in nature and in the human body. Okay, this one here is D-aldotriose, D-glyceraldehyde. OH group is on the right-hand side. That's carbon 1, 2, and 3. There's only one chirocarbon in glyceraldehyde. Okay? And in this case, OH group is on the right-hand side, so it's D-glyceraldehyde or D-aldotriose. All right. Now we've got the carbonyl group on the top. So this is an aldose. And 1, 2, 3, 4, 5, 6 carbons. So it's a hexose. That's number 1. Number 2, you always start counting from the top down. 3, 4, 5, 6. So we look for the chiral carbon. In this case, there's 1, 2, 3, there's 4 chiral carbons. We take the chiral carbon with the highest number, which in this case is number 5. And we find out the OH group is on the right-hand side. So it's a D-aldo hexose, 6 carbon sugar. D-glucose or D-aldo hexose. Okay. Again, this is a ketose. And it's 1, 2, 3, 4, 5, 6 carbons. So it's a D-keto hexose, or D or L, I should say. It's a keto hexose. And this is number 1 carbon, 2, and again, the most oxidized always goes on top. 1, 2, 3, 4, 5, 6. Again, there's 3 chiral carbons in this compound. The chiral carbon with the highest number is chiral carbon number 5. And the OH group is on the right-hand side also, so it is a D. D fructose or D keto hexose. Okay. So draw the Fisher isomers of glyceraldehyde. Glyceride is an aldotriose. Okay, so you should all be able to do this by now. Triose is a 3 carbon sugar. Okay. It's an aldose in the name, so it's a aldehyde. Okay, CH2OH at the bottom of every sugar. And this one here, we can make it, if we put the OH group here and the H here, this is a D aldotriose. If we draw the same thing, 3 carbons, CH2OH, and it's an aldehyde. And then we put the OH on the left-hand side. This is an L aldotriose or L-glyceraldehyde. Okay, so there's the compound. We get some of what I did out of the way here. This is an aldotriose. Okay. And again, the number 1 carbon's on top. That's your oxidized carbon. There's only 1 carbonyl carbon in glyceraldehyde. That's the center one. So the one on the left is a what? Is it D or L? This one here. D or L? Perfect. This one's a D. And this one is an L because the OH group's on the left-hand side. So this is D-glyceraldehyde. This is L, glyceraldehyde. Okay, draw fish projection the following molecules and for their mirror images, assign a D or an L in each name and place an asterisk by each chiral carbon. All right, so here's our compound. We're going to assign a D or an L and configuration and name to each. All right, so let's name this thing. This is, first of all, is it an aldose or a ketose?
Ketose.
Ketose. And it's 1, 2, 3, 4 carbons, right? Because this is a carbon atom right here. So it's 4 carbons. So it's a tetrose. And so it's going to be a keto tetrose. Okay. And it wants us to say if it's going to be D or an L.
D.
OH groups on the right, it's going to be a D. So D, keto dextrose. Okay. Now it wants to mark each chiral carbon. Is the first carbon, number 1, a chiral carbon right here?
No.
No. Is this one a chiral carbon?
No.
Is this one a chiral carbon?
Yes.
Yes. Is this one a chiral carbon?
No.
No. Perfect. So you have 1 chiral carbon, you marked it. So is this an aldose or a ketose?
Aldose.
Aldose, perfect. It's an aldose. Okay, it's an aldehyde group on top. There's 1, 2, 3, 4, 5 carbons. So it's a pentose. Okay. And how many chiral carbons are there in this compound? That'd be a typical test question.
3.
3. 1 right here, 1 right here, 1 right here. The one with the highest number, this would be carbon number 1, 2, 3, 4, 5. So one with the highest number would have the OH group determine the D and L configuration. So as written, this is an L, aldo pentose with 3 chiral carbons. And you could switch this OH around to make it your mirror image. Okay. Now don't forget, when you switch those, you're going to switch all these too. Every chiral center is going to switch. So everything switches over. Okay. So the new one would have, on this side, it would have OH, it would have OH, it would have OH, and then the hydrogen would be here. So when we do it, there's our mirror image. Remember, the mirror image is going to be the closest side. So everything switched at the chiral centers. Every chiral center switched. Does that make sense? So if this is our starting compound right here, okay, the OH went from the right to the left. The OH went from the right to the left. OH went from the left to the right. Because if that's our mirror, that dividing line, the one that's closest to the mirror is going to appear closest to the object. Okay, so it switches everything at a chiral center. If it's not a chiral center, it's not going to switch. It only switches the chiral centers. Okay, so like we said, this one on the left is going to be L. And this was 1, 2, 3, 4, 5 carbons, right? L, aldo, pentose. The one on the right is going to be D, aldo, pentose. But remember when you write them, because if there's more than one chiral center, every one of those is going to switch positions when it goes to the mirror image. Everyone's going to switch sides, but only the chiral center switch. Nothing else switches. Okay, there's your 3 chiral centers, which we talked about, and there's your 3 chiral centers. And every mirror image, the H and the OH change at every one of them. L, aldo pentose, D, aldo pentose. Okay, here's our next one. Okay, we're going to use a left and a right. Remember, we're going to do the mirror images of it. So this is a ketose, and it's 1, 2, 3, 4, 5, 6 carbons. So it's a hexose. So it's a ketohexose. Okay, how many chiral centers do we have?
Three.
What's that?
Three.
3. Perfect. We have exactly 3. We have a chiral center here, chiral center here, and a chiral center here. Okay, this is the most oxidized end. So 1, 2, 3, 4, 5, 6 carbons. Okay. The chiral carbon with the highest number is carbon number 5. Okay. The OH group in this case is on the right. So this is going to be a D keto hexose. And if we do our mirror image, let's see, we can put our mirror image right here. Everything else stays the same. CH2OH, CO double bond. And then this comes down to CH2OH. Okay, and there's 3 carbons. The H goes here, OH here, and OH here. And this is our hydrogen, hydrogen, OH. Every one of these switches around every chiral carbon. When it's a mirror image, it switches to the non-superimposable side. So that's going to be L, ketohexose. And this is what we got. This is the mirror image. You can see how the OH is switched. The OH has gone from the right side to the left side to the left side to the right side. Every one of those has switched for each chiral center from the mirror image. Okay, our chiral carbons, we said were located at those 3 and those 3. Okay, and we said this, the one on the left was the D keto pentose. Oh, hexose, 6 carbons. And the one on the right was a D keto, L keto hexose, because the LH group is on the left-hand side. Right? And those how our mirror images work with naming those compounds. Next one. Next one's very straightforward. Okay, there's only one chiral center, right?
Yeah.
Okay, so this is going to be on the right. So this is our D. And then our mirror image, it's going to have this switch to OH over here and then H over here. That's going to be RL. That's the only difference between them. Okay, so here's our mirror image. OH is on the right, OH is on the left. Okay, so these are going to be, this one's going to be it was on the right, this is a D, and it's an aldehyde. Doesn't look like a D, does it? D, aldo, and it's 3 carbons, triose. And it's going to be L, aldo, triose. 1 chiral center, D aldo triose, and L aldo triose. Cool. All right, a little bit longer one here. 1, 2, 3, 4, 5, 6 carbons. The same thing. How many chiral centers does this sugar have?
3.
Exactly. You got it. It's got 3. Okay. The carbon with the highest number, the chiral carbon with the highest number is number 5 right here. So OH is on the right. So this is going to be a D. And it's going to be a ketose. and has 1, 2, 3, 4, 5, 6 sugars. So this one that's shown will be a D. The other will be an L, ketohexose. And when we do that, all the OH groups are going to be on the left-hand side when we do the isomer, the mirror image of it. They're all going to transfer to the left side when it goes to the mirror image of it. Okay, so here's your 3 OH groups, all on the right. Here's your 3 OH groups, all on the left. Because you have the mirror image, it's the side closest to the mirror that's going to reflect first. And again, this is your D, ketohexose. This is your L, ketohexose, with 3 chiral centers on each one. So D ketohexose, L ketohexose. And one more, I think. 5 carbons. Okay. This one has the OH group on the left. Remember, every one of these is going to switch when you do your mirror image form of it. So this is your L, and this is an aldo, and this is a pentose, 5 carbons. There's still 3 chiral centers. Each one of these is a chiral center. Okay. OH group is on the left, so it's lever rotary, okay, which is an L. So this is L, aldo, pentose, 5 carbons. We switch around, it's going to be D, aldo pentose. Again, there's 3 chiral carbons on each one. The one on the left is an L, okay, aldo pentose. The one on the right is a D, aldo pentose. And every one of these switched, every single OH group. This OH group, this OH group, this OH group. This went from the left here to the right. This went from the right to the left. This went from the left to the right. So every group switches on the chiral carbon. The others just stay the same because they're superimposable. So it's a chiral carbon, every single group switches, not just the highest number, not just the one we're using to do D or L determination, but every group switches. That's on the chiral carbon. So explain the difference between the D and L designation and the plus and minus designation. Okay, the D designation is your positive, rotates to the right. L designation is your negative, rotates to the left. Okay, so D stands for dextrorotary, designated with a plus sign, rotates plane, polarized light in a clockwise direction to the right. L stands for lever rotary, okay, designated with a negative sign. It rotates a plane of polarized lights in a counterclockwise direction to the left. Okay, plus and minus are not adding and subtracting in this case. They're just different designations of what it is. One's a plus, one's a minus. And biological monosaccharides. All right, glucose. Glucose is the most important sugar in the human body. That's what our brain uses for fuel. The brain has to have glucose to function. Okay. It's found in many foods. Several common names include dextrose and blood sugar. That's glucose in the blood. Its concentration in the blood is regulated by insulin and glucagon. Insulin takes takes sugar out of the bloodstream. Glucagon puts sugar back into the bloodstream. You have to be able to control both to regulate it. You have to be able to put more in or take more out. Insulin absorbs sugar from the blood into the cells. Glucagon takes sugar out of the cells into the bloodstream. Okay. It is broken down in glycolysis and other pathways to release energy for body functions. We're going to study a lot about glycolysis and the breakdown pathways, how many ATP are produced and everything by breaking down glucose. We break down glucose into carbon dioxide and water is the final result. We break it down and it produces a net increase in ATP, which the body uses for energy. That's glycolysis, the breaking down of glucose. Concentration of glucose in the blood is critical to normal body function. It's carefully controlled by hormones, insulin, and glucagon. Like I said, insulin lowers your blood sugar, glucagon raises your blood sugar. Okay. Normal blood glucose levels. Okay. As a nurse, okay, as a physician, okay, as a PA, you need to understand your patients should have between 100 and 120 milligrams per 100 milliliters of blood for the glucose level. Highest concentrations would appear after a meal. That's when the most sugar gets into the body. Okay. Insulin stimulates the uptake of excess glucose by most cells of the body. And after 1 or 2 hours, levels return to normal after a meal. Okay. If blood glucose concentrations drop too low, your patient will feel lightheaded, feel shaky. Okay. When this happens, glucagon stimulates the liver to release glucose into the blood and reestablish your normal letters. Okay. So when it gets too low, the liver releases glucagon. The body releases glucagon, which tells the liver to release glucose into the blood to raise those levels up. Okay. Under physiological conditions, glucose exists in a cyclical hemiacetal form. Remember hemiacetal forms we talked about? And it's going to be a cyclic hemiacetal form, where the C5 hydroxyl group, OH group, reacts with the C1 aldehyde group. So it folds over on itself between the C5 and the C1 group. Okay, we're going to learn how to draw these too. The two isomers are formed, which differ the location of the OH group on the acetylcarbon, which is carbon number 1. Okay, these are for aldehydes, aldoses. These isomers are called alpha and beta D-glucose. In an alpha, the OH group is down. In the beta, the OH group is up. That's how we designate those two. Okay. These two isomers differ from one another location of the OH group attached to the hemiacetal carbon, which is carbon number 1. And I'll show you exactly how we do that. Such isomers differ in the arrangement of bonds around the hemiacetal carbon and are called anomers. We talk about alpha anomers. Okay, the hydroxyl group is below the ring, goes down. The beta anomers, the hydroxyl group goes up on the ring. We'll show you that in just a second when we get to the ring structures. So the alpha and beta forms can be distinguished from one another because they rotate plane polarized light differently. Okay, that's you can tell them apart. Glucose is an aldohexose, 6-carbon sugar, C6H12O6. That's glucose. It's an aldohexose, so it's an aldehyde with 6 carbons. Okay, and it's a cyclical form of how it exists in the body. Okay, the Fisher projection shows the stick form of it in a linear form. The Hayworth projection shows the cyclical form. Okay, this is a cyclical form of D-glucose. And what happens is this is your carbonyl, carbon right here, okay? And the oxygen from this is not a good picture of it. The oxygen from the lowest, where you do your D or L enantiomer from, incorporates into the ring structure. Okay, and the CH2OH goes up on top. It's how you draw it from the ring structure. It's how you draw it. And we'll show you how to draw in just a second here. It's just how it incorporates into it. So the oxygen here, that's the oxygen from the one that determines your D or L enantiomer. Okay, binds to this carbon. This becomes an OH group, and this OH group from the carbonyl carbon is either going to be up or down. If it's below the ring, this is alpha. If it's above the ring, that's beta. We should know how to draw from the line structure to the cyclical form. Again, this is a 6-carbon sugar. So it's a 6-member ring with oxygen replacing one of the carbons, and the CHO2 goes up on top to the left of it. every time. So there's your alpha form. There's your beta form. Okay. This is how the ring forms. This is our typical Fisher structure, open chain. Okay. This is the carbon atom that determines the D or L isomers. So this oxygen here is this oxygen here. That's the one that gets incorporated into the ring. So if you look at the incorporation, you have the CH2OH right here going this way. Then going back up, you would have the different structures. This is your carbonyl carbon. This is this OH. Okay. And it's going to be either up or down, depending on just random choice. If it's down, it's alpha. If it's up, it's beta. Okay. And the rest of the ring structure as it comes across, this is carbon number 2. This is carbon number 2. If the OH group is on the right-hand side, it goes down. If the OH group is on the left-hand side, it goes up. OH group on the right-hand side goes down, and this OH is gone. This is the one that incorporated into the chain. So that's how they get these chain structures, these cyclical structures. Okay, just like we did. The oxygen of the OH group that forms your D or L designation is part of the ring. Then the CH2OH is always up to the left of the oxygen. And then going down the ring, if it's on the right side, it goes up, it goes down, I'm sorry. If it's on the left side, it goes up. Okay, and that's how you make a ring structure. Okay, so this is a this is 6 carbon ring. It's a 6 member ring structure. Okay, so draw the structure for D-glucose. Okay, glucose is D-aldohexose. So let's just take some time. I want to show you how to draw this here. It takes some practice, but you learn how to do it. An aldohexose is a 6 carbon sugar with an aldehyde group on top, right? We know that already. So this is our aldehyde. And it's 6 carbons. 1, 2, 3, 4, 5, 6. CH2OH. Okay. It's an aldohexose. So the OH group is on the, this is a D, so it's on the right. So OH, and the other one's D-aldohexose. Where's the rest of them go? Okay, okay, so we're going to draw that. I wish I could draw it on this side. So you drew 6 carbons, like I just draw in a straight line. Each is separated from the one by the bond. Okay, so here's your 6 carbons. Okay, the most highly oxidized one is drawn at the top, like we said before. Carbon 1 is the aldehyde. At the bottom is a CH2OH. So here's your aldehyde group, and here's your CH2OH. Okay, then you know it's a D-glucose. So the OH group, the carbonyl carbon with the highest number, the OH group is to the right-hand side because it's a D. It was L to be on the left-hand side. So we're going to form the ring structure. Remember, the one that determines the D or L, the highest carbonyl carbon, this oxygen is going to be part of the ring. And this is going to sit above the ring. So you're still going to have 6 points on the ring. 1, 2, 3, 4, 5, and 6. We're going to have the oxygen incorporated into the ring. And we usually always draw the oxygen just by designation to the top right. There's your oxygen. There's your ring structure. Okay, 6 carbon, 6 membered ring. The CH2OH is this right here. That goes up above the ring. Then this is your number 1 carbon right here. We'll put the OH group up because we'll do beta first. This is your beta. Okay. And then the other ones are going across like this. Now this is like a three-dimensional ring here. So kind of draw that a little thicker there. So it kind of stands out a little bit. Okay. So going from down the ring, this is your number one carbon right here. That's this point where that was going. So number two, the OH group is to the right, which means it goes down. OH group is to the left, which means it goes up. OH group is to the right, which means it goes down. And then fill in your hydrogens. That's the ring structure. That's how you draw a ring structure. It's going to take a lot of practice, but you'll get the hang of it. It's just, you got to realize you're incorporating the rings into it. Then the left ones are going to go up, right one's going to go down. Your CH2OH goes up behind it, and this is beta. Now the alpha ring would be the same thing. Okay. That's a hydrogen right there. Hydrogen. Okay, except the OH group now goes down because when the ring folds over, there's a 50-50 chance of going up or down. And that's your alpha. OH groups are in the same position. Okay. And those are the two cyclical structures that you get from D-glucose, the alpha and beta. And you know it's D-glucose because when you started, you had this on the right-hand side. Okay. We'll do a lot more examples like that. So the position of the hydrogen and hydroxy groups on the remaining carbons must be learned for each sugar. Every sugar is going to be different. Okay. So draw the structures of D-ribose and L-ribose. Okay. And it tells you ribose is an aldopentose. For D-ribose, the hydroxyl groups are C2 and C3 are on the right-hand side. Okay. So let's do D-ribose. Okay. It's an aldopentose. So 5 carbons. Right? Bottom is CH2OH. Top is your aldehyde group. So far, so good. It says it's D-ribose, so it means the carbonyl carbon with the highest number, the OH group is on the right-hand side. Okay. And it also tells you at C2 and C3. Okay, C2 and C3, these are these right here. That's C2 and C3. Okay, it says for the hydroxyl groups at C2 and C on the right-hand side also. So OH, OH. Okay, so now you've drawn D-ribose. You should all be able to do that from that information above. Realize it's an aldehyde, 5 carbon sugar. D-ribose means the OH is going to be on the right-hand side on the highest number carbonyl carbon. Then the other 2 remaining ones are C2 and C3, and it tells you they're on the right-hand side. Every sugar, those are going to be different. So I'll let you know what those are. Now, draw the ring structure of it. This is a 5 carbon sugar. So it's going to be a 5-membered ring, not a 6-membered ring. So 5-membered ring, put the oxygen on the top. There's your 5-membered ring. And again, this will be a little bit thicker here. Make it look a little more 3-dimensional-ish. Like I said, I'm not a great artist by any stretch of the imagination. But make that a little thicker there. Okay, so there's your 5-member ring with oxygen incorporated. This is the oxygen that's in the ring, this one right here. Okay, you go back 1. It's going to be your CH2OH. So there's your attachment, CH2OH. and H. Okay. This is the one that determines whether it's alpha or beta. So D-ribose will have an alpha D-ribose and a beta D-ribose. Okay, so this is a carbonyl carbon right here. This carbon is this carbon right here. So let's put the OH group and the H group. And this is C2 and C3. At C2, the OH is on the right-hand side. Right-hand side means what? Up or down? Right-hand side means below the ring, means down. And this is alpha, beta D ribose. Okay.
If it's not on the same side and the cyclical structure, then how come it's not reversed on the condensed structure? Like, so we have the two OH are on the right side,
Right.
and then the OH that's next to the double bond with the oxygen is on the top though. So
This
on the
is-
left, how come it's not on the left?
This isn't a carbocarbon.
Oh, okay.
So and when you form the ring, that goes up or down, 50-50 chance.
Okay.
That gives you alpha and your beta. Does that make sense?
Yeah, so you're never gonna see where it's like HC double O bond and then OH on the left of that first or
Sure you
second
could.
carbon.
Sure you could. That's this OH group here. This one here is this OH group right here. Remember this OH group here that determines alpha or beta is from this oxygen right here. That hydrogen has connected to it to form an OH group.
Oh, okay.
Like I said, this takes a lot of practice, but it will make sense. It just takes, you got to just practice drawing a couple times. And we'll do a bunch of examples here.
Okay.
So far, so good. And if I want to do the alpha D ribose, I would have the oxygen. Okay, and my CH2OH always goes up. And then the OH group would go down here. And this would be alpha D ribose. And then the OH groups would still stay the same position. Because again, those are on the right-hand side, so they go down. And there's your hydrogen. So those are the two beta D ribose and alpha D ribose. Okay, so you got to draw this first to determine this and this. Okay, draw the structure for D-galactose. Okay. Hydroxyl group at C2 on the right-hand side. It's an aldohexose. Okay. So it's an aldehyde, 6-carbon sugar. Okay. So this is D-galactose, which is, here's your 6 carbons. 1, 2, 3, 4, 5, 6 carbons. Okay. The highest carbonyl carbon has the OH group on the right-hand side. That's your D. It says carbon number 2 is on the right-hand side. 3 and 4 would be on the left-hand side. That's by default. Okay, so that is D-galactose. Okay, you should all be able to draw that structure from what's given up above. Okay, and then we'll make the cyclical form of it. Okay, draw the structure of L-galactose. We'll draw the cyclical forms in the next problems, I think. So it's an aldohexose, carbonyl group C2 on the left-hand side. Okay, aldohexose, 6-carbon sugar, aldehyde group at the top. Here's your aldehyde group, 6-carbon sugar. Okay, and it's an L. So the OH group is on the left-hand side for the highest carbonyl carbon. Okay, then it says C2, it's on the left, and the other ones would be on the right then. That's L-galactose or L-aldohexose. Draw the Hayward projections of alpha and beta D-glucose. Okay, now we'll start drawing the circles, the cyclical forms of it. This is the open chain. That's how they form. Again, this oxygen is what gets incorporated into the ring. This hydrogen forms to that oxygen to form OH. And this OH group is the one that at C1 that becomes your alpha or beta, depending how it forms. See, if it comes down like this, it's going to form the alpha. If it goes up like this, it's going to form the beta. This is going to be alpha. That's going to be beta. And you can see it's just a 50-50 chance of how that carbon rotates when the rings form. And that's how you form the rings. And like I said, the ones on the left go up, the ones on the right go down. Okay. So there's your ring structure. Again, kind of a little more detail on it. Okay. So this is the oxygen. This is your CH2OH group right here. It's going to go up. This is your carbonyl carbon that determines your D or L isomer. This is the oxygen that's attached to it. It lost its hydrogen. Okay, and it's going to form this ring right here. And this hydrogen is going to come from the carbonyl carbon. Okay. And the same thing either way it forms. This is the alpha D-glucose on this side and then beta D-glucose on this side. If the OH group goes down. Remember, left OH group goes up. Left side is up, right side is down. Okay. So how do you determine which group placed above the ring, which group placed beneath the ring? Okay. Drawn in. So the ones on the left side are drawn in blue. Those go above the ring. Okay. The ones on the right side on black print go below the ring. The OH group on the number 1 carbon is alpha or beta because it has a 50-50 chance of going up or down on the ring when the ring forms. Okay. So the groups on the red, those go beneath the carbon ring on the Hayward projection. Okay. OH group determines the alpha or beta position again. All right. So the cyclical form, okay, of any D sugar, the CH2OH group is always up. So this group here, like we said, is always up. The CH2OH group is always up, okay, which is a cis relationship. Okay, on this side here, trans relationship on this side here. Again, cis or trans to the OH that goes up or down, because that's the only one that moves. So this is locked into place. So this would be a trans relationship, opposite sides. This would be a cis relationship, same side as the OH group. Okay. Refer to the linear structure of D-galactose and D-ribose to draw the Hayward projections of alpha and beta D-galactose and alpha and beta D-ribose. Okay, so D-galactose. D-galactose, there's your form for it. There's 1, 2, 3, 4, 5, 6. So it's a hexose and it's an aldehyde. So it's an aldohexose. Okay. And it is a D-aldohexose. So everybody should be able to come up with this term right now. D-aldohexose. And should be able to write that from that. As long as I tell you where these other OH groups are going to go. Okay. That's D-galactose or D-aldohexose. Now it's a 6-carbon sugar. So it's going to be a 6-member ring with oxygen replacing one of the carbons. Okay, so it's 6 carbons, we're going to have a 6-member ring. So you draw your 6-member ring. Just by default, we put the oxygen in the top right-hand corner. We just always do that. Okay. That's going to be a little thicker there just to make it. So far, so good. 6 carbon, 6-member ring. The CH2OH group always goes up. Okay. Okay, there's your CH2OH and your hydrogen. And this is your carbon. Now, this is your carbon number 1. This is this one right here. Okay, if it goes up, it's beta. And then we'll go to the next carbon, which is this one here. Where's the OH group? It's on the right-hand side, so it goes down. We go to the next carbon. Where's the OH group? It's on the left-hand side, so it goes up. And then the next carbon, OH group to the left-hand side, it goes up. And then put our hydrogens in. Okay. And that's beta D-galactose. Okay, so that's how you determine how to draw the cyclic destructor. You have to draw those for the final, or have to recognize those when I draw them. I'd be able to pick the correct structure if I give you the numbers. And to draw the alpha form, okay. There's your attachments. CH2OH goes to the left and it's always up. There's your hydrogen. The OH group now, remember this is the carbonyl group. This is that oxidant formed the ring. We've got the hydrogen on it, so it can go up or down. The other ones are locked. And this is alpha. And the OH group is going to stay in the exact same position. OH group, H, H, OH, OH, H. Okay? So there's your beta D-galactose and your alpha D-galactose. So when you practice, you're gonna have to practice drawing these. You're not gonna get just listen to me talk. But when you draw the rings, remember this oxygen, the OH group that determines your D or L isomer. That's what the oxygen that is in your ring. Okay, that's gonna bond to this carbon right here. And that's this oxygen right there. That's in your ring. And this OH, this hydrogen, is going to bond to that oxygen to form your OH. That's the OH group. That goes up or down. That determines your alpha or beta designation. And then once you form the rest, okay, if the OH group, if the group is on the left, it goes up. If the group is on the right, it goes down below the ring. And those are only 3 that are left. And that's it. That's all there is to drawing a ring structure. Like I said, it's going to take practice, though. Don't just rely on me talking about it. So practice it. And that's D-galactose. And there's a better form of it. It's prettier. Okay. Again, your OH group was on the right, on the left, on the left. CH2OH goes up. And this OH went down. So that is your alpha D-galactose. Your beta D-galactose is going to be the exact same thing with the OH group up. Everything else is in the exact same position. This oxygen is from the Fisher projection of the highest number chiral carbon, the one that determines your D or L isomer. That gets incorporated into the ring. Okay, and that's a beta D-galactose, like we just drew. Again, it's a little prettier picture than I can draw. I draw better on the computer. Okay, and it's beta because this OH is above the ring. Alpha is below the ring. D-ribose. Okay, there's your ribose. Ribose is a 5-carbon sugar. Okay, so I would say on the exam, I would say draw the Hayward projection for D, aldo, pentose, And I'd say with C2 and C3 hydroxyl groups on the left, on the right side. With that information, you should be able to draw this structure. A D-aldopentose, 5-carbon sugar, aldehyde group at the top. Okay. The OH group on the highest carbon here, that's the D. It's going to be on the right. And then I told you C2 and C3. This is carbon 2 and carbon 3. The OH group, hydroxyl group, is on the right. So you should be able to, from that information, this is how your exam is going to look. That's what it's going to say. So I don't want you to remember what ribose is. I don't want you memorizing sugars, but I want you to be able to identify that and be able to draw that. And once you can draw that, now you can draw the Haworth projection. So if the question says to draw the Haworth projection, realize you have to draw the Fisher projection first before you can draw the Haworth projection, because you have to know how it's going to line up. So this is a 5-carbon sugar. So 5-carbon sugar is going to be a 5-member ring. Glucose was a 6-carbon sugar, 6-member ring. Ribose is a 5-carbon sugar, 5-member ring. So on the 5-member ring, oxygen goes on the top. It just makes it easier. There's your 5-membered ring. Let's make these a little thicker so it kind of looks 3-dimensional, but probably not really. Okay. Everybody good so far? 5-member ring. This oxygen right here is this oxygen right here. Okay. Are we good so far? Everybody understands how I got a 5-member ring and where the oxygen came from that's in there. Can you give me a thumbs up or yes or something? All right, perfect. Cool. So there's your ring. Now we know to the left of that, because we're going down here, the CH2OH is always up for the D sugars. Okay. We know the next one going over, this is our C1. This is the carbonyl carbon right here. And we know that's going to be 50-50. So let's just put one up just because I wanted to go up this time instead of down. Okay, and we got 2 more positions. Going down this ring here, we got the OH group on the right-hand side, which means it goes down. Going down to the next carbon, we got the OH group on the right-hand side, which means it's going down. And that's it. That's all our groups. And that is beta D ribose. If I want to do alpha D ribose, I draw the same thing, 5-carbon sugar. Okay, CH2 OH. There's my attachments above and below the ring. So now OH goes down and everything else stays the same. And this is alpha because this OH group is down. Beta, that OH group is up. Okay, you just gotta remember where the elements are coming from and how it's forming the ring structure. And that's called a Haworth projection. Okay. So let's look at D-ribose. And again, these were the pictures here. And this be drawn a little bit clearer here so you can see them. Okay. This is alpha D-ribose. The OH group is down for the number 1 carbon, where the carbonyl group was. That was a carbon, that was the carbonyl group. And that determines your alpha or beta. And then D-ribose was the rest of the sugar with these 2 H groups below the ring. Now in beta, this is going to go up and everything else is going to stay the same. That stays up, that stays down, that stays down. That's the only thing that changes. And this is beta D-ribose. Like I said, OH group is still down, OH group is still down, CH2OH group is still up, but now the OH group has switched. It's gone from down below the ring to above the ring. If it's above the ring, it's beta. If it's below the ring, it's alpha. Fructose is in a lot of products. Fructose is also called levulose. It's also called fruit sugar. Contributes sweetness to ripe fruits. Okay. It's found large amounts in honey, in corn syrup, and in fruits. Okay. It is the sweetest of all sugars. Okay. If you look on any Coca-Cola can or Pepsi can, it's HFCS, high fructose corn syrup. HFCS is in a lot of products. That is just, that's the term that it contributes to diabetes, heart disease, obesity, tooth decay. It's all it is sugar, and it destroys everything. And you'll see HFCS on your soda pop cans or anything else. It's high fructose corn syrup. It's extremely sweet. It's a ketohexose, which means it's a ketone now, not an aldehyde. So it's a ketone on top, and it's a 6-carbon sugar, ketohexose. Okay. So this is the ketohexose. Now, the only difference is this is not a hydrogen anymore. Okay. So you still have 1, 2, 3, 4, 5, 6 carbons. So it's going to be a 6-membered ring. Okay. Except you got to remember this carbon is not going to be part of the ring anymore. So if it's an aldehyde, that would be a 6-carbon ring. If it's a ketone, it's going to be a 5-carbon ring, because these 2 carbons are not included in the ring structure. Okay. They're either going to be above or below the bond here. There's going to be 2 CH2OH groups. Okay. So when it's a ketone, it's 1 member less in the ring structure. Okay. Because the CH2OH groups sit above or below the ring. Okay. So the CH2OH on the bottom here, okay, so this CH2OH on the bottom is this CH2OH right here. This CH2OH is attached to the carbonyl carbon. This determines your alpha and beta. Remember, this takes this hydrogen and this slings up here, and this oxygen connects to that carbon. So this is 1, 2, 3, 4, 5-membered ring. Okay, that's why this one's a 5-membered ring when we're dealing with ketones. Okay, same thing again. This goes up. This is your carbonyl carbon right here. If the OH is down, this is alpha. If the OH group is up, this is beta. Okay, and the OH group from the first OH group, let's do right here, this first OH group right here. Sorry. This first OH group right here is on the left, so it goes up. The second OH group is on the right, so it goes down. Okay, same rules apply. The only thing we have different now is our OH group does not have a hydrogen here. It has a CH2OH because it's a ketone. Okay. But still, if the OH group is down, it's alpha. OH group is up, it's beta. So instead of hydrogen, we have a CH2OH. That's the only difference now. If it's on the left side of the ring, on the left side of the Fisher projection, it goes above the ring. If it's on the right side, OH group, it goes below the ring. Okay. So that's D-fructose. That's the alpha form of alpha D-fructose. That's the beta form. That's beta D-fructose. Okay, so don't get confused with there's a ketone there now, because the only difference is we're going to put CH2OH opposing the OH group instead of hydrogen. So this is not a hydrogen anymore. If it was a hydrogen, it'd be an aldehyde. We just put our hydrogen there. So that's the only difference. Everything else stays the same. Don't get confused with it. We just put CH2H instead of hydrogen. Everything else remains exactly the same. Okay. Galactose. Okay. Galactose is the principal sugar found in mammalian milk, in breast milk, is galactose. It's an aldohexose, very similar to glucose. So it's aldo, so it's an aldehyde. Hexose is a 6-carbon sugar, just like glucose is. Okay, beta D-galactosamine is a component of the blood group antigens. That's what determines your A, B, and O blood groups. Okay. So this is real close to glucose. This is D-galactose. And it's D because the OH group on the highest carbonyl carbon, remember this is number 1, 2, 3, 4, 5, 6. So now we're back to our hydrogen. The highest numbered carbonyl carbon is number 5. The OH group is to the right. So this is a D galactose. It's a D aldohexose, aldehyde, and 6 sugar carbon backbone. Okay. So now if we look at this cyclic form, this is going to be a 6-carbon or a 6-membered ring again. Notice we got 6 carbons, and the only one that's not going to be in the ring is the CH2H, but this oxygen here is going to be in the ring. That's your oxygen for the ring. Okay. That oxygen is this oxygen right here. And this carbon number 1 is this carbon number 1 right here. And that's what determines your alpha or beta. So if we look at the ring structure, we have our OH group, in this case is up here, in this case is down. So now we got the next one. Let's find a new color. Let's do purple. We did purple. Let's do orange. Okay, so the next carbon is carbon number 2, and the OH group is on the right-hand side. So that means it goes down, which is here. The next one. Okay, carbon number 3. OH group is to the left. So left side OH group goes up. And the next one, let's go back to red. Carbon number 4. OH group is to the left-hand side, so it goes up. That's how you write them. Okay, so it forms your ring structure. So on the top one here, this OH group is down, so that's alpha. That's alpha D galactose. OH group is up on this one, that's beta D galactose. Okay. And then galactose orientation. Hopefully my screen didn't freeze again. And it's not sharing it right anymore. Okay, let's see if we can share this again. Dun, dun, dun. I don't know why this kicks off so much. It's only done it today. It hasn't done it before. Okay, we're back. All right, everybody see galactose orientation now. Is my screen back?
Yeah.
All right, perfect. So now galactose orientation. Glucose and galactose differ only in the orientation of one OH group. Okay, so there's beta D glucose. Okay, this is beta D galactose. And the only difference is this OH group right here. On galactose, the OH group is above the ring. On glucose, the OH group is below the ring. That is our only difference. Ribose, deoxyribose, 5-carbon sugar, make up the backbone of DNA and RNA. Ribonucleic acid, RNA. DNA is deoxyribose nucleic acid. Okay, they're compounds of many biologically important molecules. Our whole genetic system is based on those two molecules. Okay, exists mainly in the cyclical form. Okay, they're an aldopentose, 5-carbon sugar with an aldehyde group at the most oxidized end. Okay, so this is alpha D ribose for the your ribose sugar. And again, this is your CH2OH. And again, we use different colors. That seems to help what people are saying. CH2OH, there's your CH2OH. There's this oxygen. Right here is this oxygen right here. It's a 5-carbon sugar with a 5-carbon ring because it's an aldehyde. Remember, if that was a ketone, it'd be one less carbon in the ring because the CH2 groups go above the ring. Okay. So then we form our carbonyl group. Okay, that's from this carbon right here. If the OH goes down, this is the alpha form. Okay, so the next ones we go down. This is carbon number 2. This is carbon number 2. The OH group is on the right, so it goes below the ring. This is carbon number 3. This is carbon number 3. Okay, the OH group is on the right, so it goes below the ring. That's it. That's how everything matches up when you're drawing your ring structures. Is that making more sense with the different colors now?
Yeah, that helps.
Okay, good. Perfect. Because it is confusing to look at it first, but once you do it a couple of times, it will come to you because it's all the same pattern as you form these rings. Okay, but this is alpha because the OH is down. D, because this OH group was on the right. And ribose is your 5-carbon sugar. Okay. Replace this OH group right here with an H, and you have deoxyribose. Deoxy means you got rid of an oxygen, deoxy. And there's no number there, so it's a carbon at the number 1 position. So if you replace the oxygen, if you lose an oxygen at carbon number 1, it's deoxyribose, which is the sugar for the DNA background. Deoxyribose nucleic acid, DNA. Okay. So I take this OH group here, the one from the carbon number 1, that was my carbonyl carbon. If I replace that with a hydrogen, I now have deoxyribose for my sugar. Okay. So beta D2 deoxyribose, one of those components of the sugar phosphate backbone of the DNA molecule. Okay. In this molecule, OH group at C2 has been replaced by a hydrogen. The designation 2-deoxy indicates the absence of oxygen at the number 2 carbon. So now the OH group on my carbonyl carbon is still here, but now my number 2 carbon, the one down below it, now I have my OH group has been replaced. Okay, and then you get 2-deoxy, which means you're missing an oxygen at the number 2 carbon now. And this is the beta because this is above the ring. And remember, beta, the OH group is above the ring at C1. Alpha, the OH group is below the ring at C1. Okay, and what you're looking at on the screen there is beta D2-deoxyribose. So breaking it apart, you have your ribose, which is your 5-carbon sugar. You have the beta form, which means this OH group is on top. you have the D, which means the highest carbon, highest chiral carbon, had the OH group on the right-hand side in the Fisher projection. And 2-deoxy means you've moved an oxygen at the number 2 carbon. Okay, so beta D 2-deoxyribose. Okay, reducing sugars. Okay, these are sugars that are important in determining diabetes and testing your patients and why they cause reduction of things. So the aldehyde groups of the aldoses are oxidized by Benedict's reagent, which is an alkaline copper 2 solution. Okay, this is when you urinate in a cup and they're able to put sticks in and determine whether you have glucose or ketones spilling over into your urine. Okay. So the blue color reagent phase as reaction occurs, reducing Cu2 plus to Cu plus 1. That's a reduction operation. If something's being reduced, that means your sugar is being oxidized. Okay, because remember, oxidation reduction reactions always occur together. So it starts off as blue and goes to a red-orange precipitate that forms copper oxide. So the test can measure glucose in your urine, which you should not be spilling glucose in your urine. If you are, it means glucose is too high in your bloodstream. It's not being absorbed by your cells, so you have a type of diabetes. And here's a reduction reaction. Copper goes from +2 to it's +1 in this case here for your oxidation number. Okay, so copper is being reduced. That means your sugar is being oxidized. So here's your sugar, your aldehyde group. Okay, and you're adding oxygen to it. You're going to carboxylate salt form. Okay. So the sugar is being oxidized. The sugar is causing reduction. Remember, when one happens, the other one happens. Okay. You always have oxidation reduction occurring together. And this is going from a blue color to a red-orange color. Okay. But notice your sugar is being oxidized. Copper is being reduced. Okay. So all monosaccharides and the disaccharides, except for sucrose, are reducing sugars. Reducing sugars means they're being oxidized by themselves. They are being oxidized, okay, but they're causing reduction of another compound. In this case, it's the copper. Okay, so all monosaccharides and all the disaccharides, except for sucrose, are reducing sugars. They cause reduction. Now the ketoses normally can't reduce like we had before, but they can isomerize to aldoses and they can also cause reduction, okay? Because you have isomerization reactions. So although ketones generally are not easily oxidized, ketoses are an exception. So sugars that have ketones are the exception, okay? Because the OH group on the carbon next to the carbonyl ketones can be converted to aldoses under basic conditions, like ene-diol reactions. Remember the double bond being formed and then 2 OH groups being formed. We did it before with our hemi-acetyl groups and hemi-ketyl groups. We had that intermediate structure. So this is D-fructose. D-fructose, again, that's your D form there, is a 6-carbon sugar, but it'll be a 5-carbon ring, okay, because there's an extra CH group on the top, because it's a ketone group. Now, ketone groups cannot be oxidized, but what's happened is the OH group, the double bond from the oxygen, okay, where am I? I can swing up to that carbon from a double bond there, and then this hydrogen can form right there. That forms your COAs. Let me do a little bit better here. Maybe we can follow a little bit better this way. So this oxygen here, the double bond forms under there, and then one of these hydrogen are going to form onto the carbonyl carbon here. Okay, that's an intermediate step. Okay, that's your enediol. Okay, di is two OL, two OH groups, and an ene. It's an unstable compound. Okay, and it could slam back here. The double bond can form. Okay, and that forms your carbonyl. I'm sorry, I wrote that wrong. The bond can swing up and form your H group, and this hydrogen can come down. Okay. So what you've done by moving the double bond, you move the double bond from the oxygen up, okay, then up to the other oxygen, up to this oxygen right here. So it's gone from this oxygen to this oxygen. Okay. So what it's basically done is form an aldehyde from a ketone. Okay. We did this before with our enediols, the same reaction. Okay, and these enediols are extremely unstable. They're going to either form the bond back that way or back this way. So some are going to form back to the D-fructose, some will form back to the D-glucose. But now if you form this in solution, okay, this is an aldehyde. Aldehydes are reducing sugars that cause reduction. So if D-fructose is in the blood, you will still get a positive reaction. Okay, so you can convert a ketone, as long as it's a ketose, which is a sugar, into an aldose. So basically what you're doing is you're converting a ketose, which is non-reducing, to an aldose, which is reducing. So sugars, the ketones in sugars can reduce also because of this enediol formation, where you have an unstable intermediate by forming a double bond on the carbon, and you can switch where the double bond is on the oxygen. So all you've done is move the double bond to the oxygen up one carbon and convert it to an aldehyde. And now this is a reducing sugar. And it's through that enediol transformation. So for many years, Banach was used to test for glucoseuria, glucose in the urine. Okay. Individuals suffer from type 1 diabetes, which are dependent diabetes mellitus, do not produce a hormone insulin. If you're type 1, your pancreas, their alpha islets don't produce insulin. So it controls the uptake of glucose from the blood, like we talked about before. So type 1, you don't produce insulin at all. When the blood level rises above 160, okay, the kidney is unable to absorb the excess, and then glucose is found in the urine. So if your patient has a blood sugar of, say, 200, okay, you know that sugar is being spilled into the blood, not being absorbed by the cells, okay, because you're not producing insulin, and now spilling into the urine once it gets above 160. And once it's in the urine, we can measure it. Okay. The level of blood glucose can be controlled by injections of insulin. Urine glucose levels are monitored to ensure that the amount of insulin injected is correct. Gives you the correct amount of insulin injected. Okay, so the Bendix reagent was a useful tool because the amount of copper oxide formed, and hence the degree of color change in reaction is directly proportional to the amount of reducing sugar in the urine. In other words, if there's a lot of sugar, you get a lot of red color. If there's a little sugar, like a little 160, you get a little bit of red color. So the color spectrum is used to determine how much insulin is spilling over into the urine from the bloodstream. Okay, so a brick red color indicates a very high concentration of glucose in the urine. Okay, a yellow, green, blue-green solution indicates decreasing amounts of glucose in the urine, and a blue solution indicates an insignificant concentration. Okay, so use of Bendix reagent to test urine glucose levels has largely been replaced now by chemical tests that are much more accurate. So now we just use chemicals. The most common technology is based on a test strip that's impregnated with the enzyme glucose oxidase. Okay, and it will cause a measurable color change. So we use glucose oxidase, which is an enzyme. In one such kit, the compounds that result in color development include the enzyme peroxidase. Okay, peroxidase, a compound called orthotolidine, which is a yellow dye. Okay, when a drop of urine is placed on a strip, the glucose oxidase catalyzes conversion of glucose into gluconic acid and hydrogen peroxide. Okay, The tester remains yellow if there's no glucose in the sample. Okay. It varies from pale green to dark blue, depending on the concentration of glucose in the urine sample. So again, you got a color spectrum to determine how much how much glucose is spilling out into the urine. And that's what it looks like when you're doing your sticks. This is what you use in the hospitals now in the emergency rooms. Okay. And it shows you the glucose, how it increases into the darker colors. So with the proteins, you're spilling proteins, you're spilling ketones, ketoacidosis, you spill ketones into urine, and it can also test this for the pH, the acidity of your urine. Okay, so you get all that with just one stick. Frequently, doctors recommend that diabetes monitor their blood glucose several times a day. This provides a more indication of how well the diabetic is controlling his or her diet. So there's a lot of patients have glucose monitors, glucose meters. Okay, I use one every day or 2-3 times a day. Okay, couple the oxidation of glucose by glucose oxidase and appropriate color change in the system. And those little monitors read the color change. Those little strips they put in the monitors, you poke your finger, put a little blood on it, that strip changes the color. And there's a photometer inside these little monitors. See, as with the urine test, the intensity of the color changes proportional to the amount of glucose in the blood. Okay, you have a photometer in the device that reads the color change, and now it displays your glucose concentration. But there's no lining of a color, it's a number. It gives you a number every time you do that on your device. An even newer technology device that detects the electrical charge to generate the oxidation of glucose. Okay, if the amount of electrical charge is proportional to the glucose concentration.